And it's phenomenal, the change that I've witnessed over the last 20 years, since 2005, the first investments and my first exposure to what was going on in China to now is just absolutely phenomenal. The rate of change, the high levels of automation, the quality control is absolutely phenomenal.
We're taking the Smartery podcast on the road this week to one of the world's leading solar photovoltaic research institutes, the UNSW in Sydney. I'm your host, Jonathan Gifford. And while Australia might not seem like it's the epicenter of solar research and solar technology, Professor Martin Green and the numerous teams at the UNSW have made an outsized contribution to photovoltaic technology and manufacturing through its close ties and collaborations with the Chinese industry. So what's next? I caught up with Renate Egan at the UNSW to find out. Renate leads the Australian Centre for Advanced Photovoltaics, and she shares her insights into cutting-edge research like PV perovskites, novel solar materials, and the future of PV manufacturing, and much more. Renate has had a long career in solar research and the industry, with almost 12 years' experience at the UNSW, leadership roles at Suntech, thin film developer CSG Solar, and Pacific Solar, dating way back to 1995. And she's also the co-founder of residential PV and battery monitoring company, Solar Analytics. Thanks for tuning in to this episode of the Smartery podcast. Well, it's always been a bit of a mantra of mine that the progress that's being made by the photovoltaic industry is underpinned by technology, and technology is underpinned by research. So I'm very pleased on the Smartery podcast today to be joined by Renate Egan, who's the Executive Director of the Australian Centre for Advanced Photovoltaics, ACAP, which is a multi-institution research endeavour here in Australia. Firstly, introduce us a little bit to that, Renate.
Yeah, thanks. ACAP, on the Australian Centre for Advanced Photovoltaics, was established in 2012 by Professor Martin Green at the University of New South Wales, and it's funded by the Australian Renewable Energy Agency, also known as ARENA. And it was established to bring together all of the solar activity around Australia under the leadership of Martin Green and UNSW. A core to that program of work is Australian National University, or ANU, led by Andrew Blakis at the time. And then we also have all the other universities and institutions around Australia working on solar research. I don't want to list them all. It's a long list.
And what kind of areas are being examined?
So initially we had a remit to develop a pipeline of opportunity. So we had a really broad range of different research activities in 2012 when the industry was considerably smaller. With the passing of time and with ongoing support from the funding agency, we are focusing more on silicon technologies to drive down the cost of solar, and next generation technologies to drive down the cost. We're looking at reduced cost, improving reliability, longer lifetimes, higher efficiencies.
Okay, and crystalline silicon's really been the backbone of the solar industry for so long, and very much part of UNSW's solar research. Why has that decision been made to keep that front and centre of activities?
Because it's the dominant technology, and because UNSW has been so closely linked to the industrialisation of solar. So a lot of the students that have come through here have gone into China to set up manufacturing, to run manufacturing lines. Some of them then come back here and do research or reinvest in research back at UNSW and at ANU. So there's a really strong link in that industrialisation and the changing technologies that we maintain. We continue to add value. They come to us for advice. But the reality is we anticipate we're reaching peak silicon before 2030. So we will reach the ultimate limits of silicon technology before 2030. modules are coming off the manufacturing lines at 24% efficiencies now, routinely. And that people are producing 25% modules from 26%, 27% cells already. So within the next few years, we will have reached peak silicon. So in the process, we're also pushing the technology to its edge so it's a little bit more fragile, if that makes sense. So performance and reliability matters more, and we're putting an awful lot of effort into making sure that we get not only that peak performance, but we maintain those long lifetimes from modules. So we put a bunch of research into that area. We're also reaching peak silicon pushes us to say what's next. So we're really interested in and working in various threads on what technology is going to follow silicon.
Pushing the technology to its boundaries also applies just in a physical sense as well. These modules are huge now, which also comes with durability and reliability challenges.
Yes, both they're larger in size, and that's because the manufacturers are pushed to larger sizes for economies of scale, right? The more you can fit in the one product, the better your economies of scale. But they're also pushed by cost pressures to reduce the contents of those. And one of the victims of that is the glass thickness. So, and then you can imagine the challenges you've got there is that you're making the modules bigger, you're using thinner glass, so you're ending up with problems. And there's a feedback loop going on has been going on for some 18 months now to optimize that. What's the right size module? What's the right size glass thickness?
And a lot of testing will be required.
Yes.
Now, speaking of the industry, it is a challenging time for manufacturers with this overcapacity in the market. We've also seen China have an absolutely dominant position along particularly the crystalline silicon supply chain, but really if you look right across renewable energy, China's pretty dominant right across the board. What's your take then of geographic diversity of solar manufacturing? Energy is a strategic good.
Yes.
If you can't get modules, and solar is such an important part of your energy supply, that's potentially problematic for a nation. And then at the same time, China's enormous contribution in terms of delivering huge cost reduction, quality improvements as well, it has to be said, and just this vast scale to the solar industry. Where do you sit in terms of balancing those different factors?
So incredibly appreciative of the vast investments made in China that have delivered have driven down the cost of solar, demonstrated the technology works, demonstrated it can be produced at scale and at a low price, and it produced the lowest cost of energy known to man. Right? So hugely appreciative of that. And it's phenomenal, the change that I've witnessed over the last 20 years, since 2005, the first investments and my first exposure to what was going on in China to now is just absolutely phenomenal. The rate of change, the high levels of automation, the quality control is absolutely phenomenal. So full appreciation. Made possible by a long-term commitment and driven by a need. So China as a nation is trying to get its own energy independence, investing in its people, investing in its own economies, which is what you would like to think all the economies of the world were doing. China is doing it at scale, and we've all benefited from that. And they were perhaps a little bit ahead of the rest of the world in making that commitment to a low-carbon future and preparing for it. Now the rest of the world is trying to catch up and going, can we do it too? The question is, so I don't know the answer to the can we do it too. It's very clear that you only get those prices when you have those economies of scale, right? You can't translate and you can't innovate your way into it at a small scale with that sort of price competitiveness. So we did an analysis, in fact the University of New South Wales as part of the research program under ACAP did an analysis of the supply chain in Australia, and we made our recommendations about where the opportunity was for Australia and how to achieve it. And two key findings. One was that module assembly was a low-hanging fruit, low capital cost, can go in there. Australia has a competitive advantage or a comparative advantage in polysilicon refining. So if we can, because we have the raw materials, and we have, it's a very energy-intensive process. So we, in the future, will have a green energy supply, which will allow us to produce green polysilicon, so at the front end of the supply chain, we can produce the raw materials, and we can do the module assembly at the back end of the supply chain. But the cell processing piece, the ingoting and wafering and the cell processing piece is a part of the supply chain which is much higher risk, very fast technology evolution, and you really need to be part of a complex supply chain to really get the economies of scale, which the Chinese have nailed. So I think we'll have a global supply chain, and that everywhere in the world will have a role to play as we continue to scale up. How it exactly plays out, there's a whole lot of geopolitics in it.
Yeah, that's a really interesting vision, this kind of diverse supply chain, but people playing their part where there is that comparative advantage. Well, let's look at UNSW's role in the industry in just a moment. We'll be back in just a few moments. I'm speaking with Renate Egan, the Executive Director of the Australian Centre for Advanced Photovoltaics here in Sydney, Australia. Renate, we were talking about the Chinese industry and the amazing contribution that it has made to global photovoltaics. Of course, the UNSW itself, where we're sitting today, has played a key role in the establishment of the Chinese industry. Where are things today in terms of engaging with Chinese manufacturers, also research institutes, and also the personnel, the staff, the innovators and R&D people in the Chinese industry today?
We maintain a really close connection, a lot of it through alumni and personal relationships, which is a really strong foundation for any working relationship as well. So ACAP, the Australian Centre for Advanced Photovoltaics, has an industry consortium where we actually have a membership model where industry join, and we stay in touch with them, we keep them informed of what we're doing, where we're making progress, and hearing their challenges and how we can resource it. So we have a really close connection. Obviously, a lot of the improvements we've seen in manufacturing, in performance and cost, that have come out of the industry for the last 10 years have been learning by doing, right? Doing the same thing over and over again and scaling up and learning faster. The learning rate in manufacturing has been phenomenal. And we've been running alongside them, looking at some of the data they put out and helping with the learning processes, and then doing some of the fundamental analysis. If they observe a change, they continue with the process improvements that come with that, and then they send the materials to us and say, tell us why these things are different. So we go into the fundamentals, looking at the materials, the contact technologies, what it is that's changed about it, to try to understand the physics of what's going on in the change, and that allows them just to continue to learn faster. So they're doing what they're doing naturally and quickly, and then we do the science behind it. What's really interesting actually is because, as I mentioned earlier, is that industry can see peak silicon coming. So they're already producing 27% cells on manufacturing lines. Occasionally 27% cells, routinely preparing 25% cells, which is the record efficiency that UNSW held for some 15, 20 years, was 25%, and now they're routine in manufacturing. So the change is incredible. We can see peak silicon coming, and industry's really interested to know now what's next. And that's where we're putting a lot of our effort into supporting the industry with reaching peak silicon, but also looking beyond silicon. What's next?
Well, of course, that important fundamental research requires ongoing funding. As you said, ACAP is supported by ARENA, the Australian Renewable Energy Agency, so government, which is great. Of course, there's funding grants from the Australian Research Council, but part of UNSW's success, as I understand it, is also being able to work with industry and attract funds from the Chinese industry primarily, with the pressure that Chinese manufacturers are under at the moment. You know, we heard losses of something like 9 billion from the major manufacturers last year. Does that also squeeze R&D funding?
No, interestingly, it actually creates an opportunity. They're definitely under pressure, but the industry goes through highs and lows. So I think this is my third or fourth
I think we've been through a few.
They call it the solar coaster.
Yeah.
So we're in a downturn on the solar coaster. The industry that has a vision to the future is investing in that now, because they need to have an edge as the industry picks up again. So for the industry to pick up again, the market first has to pick up. And the sector, the solar deployments or solar sales, module sales, double every 3 years, right? So yeah, we're in a downturn now. Wait 3 years and we'll be in a excess demand situation again. And the industry had made money 3 years ago. They'll be making money again in 3 years' time. So there's a natural cycle just in anticipating that growth, investing in it, that leads to these highs and lows in the cycle. We also saw a technology change from PERC to TOPCon. So we've basically seen an investment in manufacturing capacity shift, with effectively a terawatt of TOPCon manufacturing capacity now, when 2 or 3 years ago we had 700 or 800 gigawatts of PERC. So there's phenomenal change and rapid change and decision making without full information about what the market's going to do. It's a hard industry to you need some strong backing and some confidence in the future. The other thing that's actually really important to reflect on is that the fact that the Chinese market itself has been a really substantial support for the industry growth. And there's only so long that can be sustained. The rest of the world has to step up and start to deploy solar at about the same rates that China is. China is over 50% of the world market at the moment. The rest of the world needs to step up.
And the Chinese market itself is in a little bit of a transition, which we heard about last episode on the Smartery podcast. You mentioned what's next in terms of technologies. I was up on the roof yesterday here, where there's perovskite modules out being tested, and some mini modules as well. A lot of there's a lot of activity around perovskites, and also perovskite tandems. Is that what you mean when you say what's next?
Yes. So the what next is, it's hard to imagine a thin film technology competing or taking a large share from silicon. So the cadmium telluride technologies, they're about 5 to 10% of the world market, and
CIGS is gone.
CIGS never got anything like 5% of the world market. So perovskites as a thin film technology will fall into the same category. So I'd be surprised if it actually gets much traction as a thin film technology. But the potential for seeing the perovskite material added as a second layer on top of silicon in one form or another to give us efficiencies above 30% is there, and it's significant. Now, it doesn't have to be perovskites, that extra layer. It could be cadmium telluride. It could be a material that we have not yet landed. We've got materials that are so the challenge, perovskites are demonstrating efficiencies on their own and in tandems above 30% already. So there's real promise in the perovskite technologies. What we're finding, though, is that they don't have the same stability and performance outcomes as silicon. So you can't match them at the moment. You can't put the two together because the silicon's going to outlast the perovskites. So we either have to improve the stability of the perovskites, or we have to find a material that does the same thing that's more stable. And it's a really exciting opportunity in research to be exploring that space now. And increasing pressure, you asked about industry involvement, increasing pressure from industry and interest to follow what we're doing to find out what's next. There has been activity in perovskites now for close to 10 years, and there are some players who are already have pilot production lines and are running in processes, and we are working with them on that performance and durability testing, which is perhaps the modules you've seen on the roof.
Absolutely. So this program is to actually do outdoor testing, to get the real data, not accelerated aging in real world conditions.
Yes.
And how does that work with the manufacturers?
In confidence. So we can tell you we're doing it. We can't tell you whose modules we're using or how they're performing. But we will be releasing the results anonymised, provided we have enough data to share that it's that it can't clearly be traced back to anybody, right? That's the only way we will learn, is to actually hold ourselves and others to account for performance.
Yeah, get that real world data.
Real world data. We also have to translate, because the material behaves so differently to silicon, the tests we've developed for silicon that allow us to do accelerated testing to predict outperformance don't transfer directly. We have to adapt those tests so we can do accelerated testing on these perovskites and the tandems. So there's not only are we changing the materials, we have changed the way the processes, we're changing the device structure, we have to change the way we do the testing of them. So there's actually, and for me, it's actually really important to manage expectations around delivery of this technology as well. Silicon will reach peak silicon by 2030. We will not have a stable, competitive, durable perovskite technology that's cost effective by 2030. So we've got some serious work to do to deliver on that. And by managing expectations, I want people to deploy silicon as much and as fast as they can. Don't wait for the next big thing, because we have a more urgent problem to solve to replace coal-fired, gas-fired generation with solar. So deploy silicon, learn as much as you can. We can cut a lot of costs out of the deployment processes. We should be doing that, and when we've got our perovskite tandem and our high efficiency products ready, they will translate into any project that's ahead of you. But
that's
people should not wait. Deploy silicon.
Let's get on with it. We have the technology. Yeah, I always get frustrated with this narrative that's sometimes out in the general public, like, we need a breakthrough.
Yeah.
Well, the energy transition requires no breakthroughs. We've got wonderful tools.
Well, 100%. What we have now is amazing. It works. It's cost effective. Deploy. The benefit of if we get to the next generation, when we get to the next generation technology, we will get more performance out of the same area. That's it, right? And that will drive down the cost, provided it costs you the same to make it, roughly. That will drive down the cost further, but right now, for a lot of what we do, it doesn't need to be any cheaper. This is as cheap as it gets at the moment. Any new generation should be solar. When the perovskites or with the tandem technologies, and we can get these efficiencies above 30%, that will drive down the cost of some of these really large industrial processes, some of the polysilicon refining, for instance, any aluminium refining in the data centers, anything like that we can drive the costs down when you're doing stuff at much higher scales. Then there's a cost advantage in these high efficiency tandems. But for residential households, for domestic use, for most commercial uses, silicon is enough. Deploy.
And it also applies to batteries, right? And I think that we've seen, the UNSW has been a part of that story, right? It's a series of incremental improvements that Martin Green and his colleagues were making going back to the 70s, just pushing efficiency higher, and then going into production, getting production costs lower, getting the scale in the industry, and these incremental improvements over a long period have been incredibly powerful.
Yes, yeah, exactly. And so that's really interesting. So what we have seen with the silicon technologies driving down the price have all been incremental changes. The shift to a tandem technology is a step change. That, by definition, will take longer. And if there are two competing technologies, well, there's a dominating technology in manufacture at the moment, TOPCon. There's two competing technologies ahead of us, which is heterojunction technologies, which sort of has been competing with TOPCon. It's step change, right? So which is why it's not got the traction that was considered possible, whereas TOPCon was an incremental change from PERC. The next technology is a back contact technology, so all the contacts on the back, the cell will look largely black from the front. That could be either on a TOPCon-like technology or on a heterojunction-like technology. Again, incremental change will favour TOPCon in the back contact technologies. Whether that plays out, I don't know. And then to add a tandem structure, so a completely different cell on top, that's another step change. It will take time. Take longer to do that step change than the incremental changes we've seen to date.
Well, thank you for sharing that, because I think there's a lot of excitement about perovskites and also a lot of impatience.
Yes.
I think people are saying 2 years we can expect it, but your message is very much beyond 2030.
That's how. So people will be. You can buy perovskite modules, right? They will not be the same cost competitive, and the durability needs to be. You need to evaluate the durability, and there are challenges with the technology by our observations, our own tests, our own research, and then we have this outdoor testing which is new, and the results are not off the line yet, so I don't even get to share anything with you. But about the actual field performance of perovskites. So there is a group at NREL and Sandia who've been doing outdoor testing, and that they also validate the concerns we have about long-term performance for perovskite tandems at the moment.
I understand also at the HZB, the Helmholtz-Zentrum Berlin.
Yes, yep.
An outdoor test facility. And it will be so crucial to collect this data so investors at the end of the day can be confident in the technology.
Yes, well, it won't be commercial. It, literally. So when I say that there's 5 years before we can expect a commercial outcome, I mean commercial, as in bankable, as in banks will lend you money to build large-scale projects. You can buy a perovskite tandem module now, right? In some people's perspective, that's commercial, but for me, it's not commercial until it's got its bankability, and that comes with outdoor testing and validation of those results.
And the message is, until then, let's keep deploying.
Yes, deploy silicon. Yes, don't stop.
Wonderful. Well, Renate Egan, the test facility on the roof is playing a crucial role in developing this pathway to commercialization for perovskite technology. Thank you very much for having us here, the Executive Director for the Australian Centre for Advanced Photovoltaics. Renate Egan, thanks for joining the Smarter E podcast. My name's Jonathan Gifford, and thanks for watching.